Hello, campers. This is Morgan back at you. We're going to be talking about the ideal gas law today. Now, in all of the problems that we discussed with Boyle's law, Charles' law, combined gas law, all that stuff put together, we were always talking about a gas under one set of conditions that was then changed to a different set of conditions. Now, what if we take all those ideas, put them together, and just talk about a gas under one set of conditions only? Okay? Can we paint a picture of what that's going to look like? The equation is PV equals nRT. It is called the ideal gas law. Okay? Now, pressure and temperature, we already know are direct proportion. Volume and temperature are direct proportion. Pressure and volume are an indirect proportion. Volume and moles are direct proportions. It all falls into place. And then we just have to add in R, which is going to be the proportionality constant to make this into an equation. Now, R is not something you need to memorize. It'll be printed at the top of tests. Don't worry, okay? So, here are values in different pressure units: atmospheres, millimeters of mercury, torr, and kilopascals. And we'll print this at the top of your tests, okay? Now, what forms can the equation take? Well, if we rearrange it, volume can equal nRT over P. Pressure can equal nRT over V. Moles can equal PV over RT. And temperature can equal PV over nR. Now, please do not go memorizing those. Just know PV equals nRT, and then use your algebra skills to arrive at these other equations. Okay? Now, we call them ideal gases. They don't actually exist, but we get pretty close to ideal behavior. And there will be four assumptions, or maybe four postulates, about why they are ideal. Okay? The first is that the volume of the gas is negligible. That means we can ignore it. Now, it's not true. The gas does take up space, okay? So just, the volume of the gas particles is, I should actually insert the word particle there just to be very clear. All right. Now, second thing, the particles are in constant motion. And we can even say it's a linear motion, and their collisions with the walls cause pressure. And that's a pretty good statement. It's pretty much true. Third, the particles do not interact. Not true. Actually, they do interact. But for this equation, we say they don't. And the temperature, the Kelvin temperature, of the gas is directly proportional to the average kinetic energy. Okay. So, we'll talk a little bit later on about the volume of the particles not being negligible and about their interactions. Okay, so you are likely to encounter the term molar volume. It's a memory trick. It's not some great implication of science or anything. It's just that we say, for ideal gases, Their volume is 22.4 liters per mole at standard temperature and pressure. Originally, it started out as a way of easily calculating the value of R. Okay, but now it's just a little memory trick, and it helps in a couple problems, but it's not as important as some textbooks and some teachers might map it out as being. Okay, so now let's do some problem solving. What's the pressure in atmospheres at 2 moles of O2 at 273 K if it occupies 10.00 liters? So PV equals nRT. I'm looking for P, which is nRT over V. Okay? Now, I have 2.00 moles. R, we're looking in atmospheres, so I use this value of R, 0.0821 liter atmosphere per mole K. Temperature 273 K, and a volume of 10.00 liters. Now, R helps us to get these units to cancel out nicely. And I'm left in atmospheres, and this equals 4.48 atmospheres. There we go. Okay. Moving on to the next page, and just some more problems. I'm going to do one each basically: pressure, volume, moles, temperature, so that you get a feel for it. And I'm also going to change the pressure units each time, just to show you the different value of R. PV equals nRT, and in this problem, what's the volume? So put a V there, put an N here, put a T there, put a P there. So V is the question mark. PV equals nRT. V equals nRT over P. So I have 3.00 moles. Okay. Since pressure's in torr, I'm going to use 62.4 liter torr per mole K. I'm going to put 273 Kelvin and 750 torr. All right. Torr's going to cancel. Mole's going to cancel. Kelvin's going to cancel. I'm left with liters. That's great. I'm looking for a volume. And with 2 sig figs, the way this is written, 68 liters. Okay. Don't let R intimidate you. It'll be printed at the top of your test. Not a big deal. So, what is the temperature? T, question mark. 4.00 moles N, 7.5 liters V, pressure P. So, PV equals nRT. T equals PV over nR. So the pressure is 100.0 kilopascals. The volume is 7.50 liters. N is 4.00 moles. Now, here's where it gets kind of important. Watch how I write the units with the R. Okay? Now, in this case, R is 8.31 liter kilopascal per mole Kelvin. So the mole Kelvin actually ends up upstairs in this fraction because R was downstairs. So the kilopascals, the liters, and the moles all cancel out, and we're left with a temperature in Kelvin, which is the way we should do it. 22.6 Kelvin. All right. So what's left? This time it's moles. How many moles? N. P. T. V. PV equals nRT. N equals PV over RT. So 1.500 ATM volume of 5.500 liters, an R 0.0821 because I'm in atmospheres, liter atmosphere per mole K, and the temperature of 300.0. Okay, Kelvin's gone. Atmospheres, liters, all gone. I'm left in moles, which is what I want. Cool. And this comes out to be 0.3350 moles. All right, so that's the 4 basic forms that this equation can take, and with the different units for pressures. Now, little twist. What if I gave you grams rather than moles? You got to switch it over. 6.0 grams of O2 times 1 mole, 32.00 grams, and this equals 0.1875 moles of O2. Okay? So a 3-liter flask would be 6 grams, that's mass. Temperature 22, you're going to have to convert that. Pressure is the question mark. So PV equals nRT. P equals nRT over V, which equals. Now, okay, moles. I got that, 0.1875. R. Okay, I want this to come out in atmosphere, so I'm going to use 0.0821 liter atmosphere per mole K. 22 plus 273 is 295 K. So 295 Kelvin. All right. Downstairs the volume. Okay, it's a 3-liter flask. 3.0 liters. Okay, so moles, Kelvin, and liters cancels. I'm left in atmospheres, and I got 1.5 ATM. All right. So now, actually, number 6 is what they call molar volume. Let's see if the number worked out. What's the volume of 1 mole? N. Here's T and P. I'm looking for V. PV equals nRT. V equals nRT over P. Let's see if this comes out to be 22.4. 1.00 moles times 0.0821 liter atmosphere per mole Kelvin. Standard temperature is 273 Kelvin. Standard pressure is 1.00 ATM. Atmospheres, moles, and Kelvin cancel. Liters, and when I ran that through my calculator, I got 22.4, which is cool. Okay? Now, standard temperature isn't normally 273, but it is for this definition. Normally we work more about 25 degrees. So let's do the same problem now at 25 degrees and see how the volume will be a little bit bigger. So it's still 1.00 moles. It's still 0.0821 liter atmosphere per mole K, but this time it's 298 K. All right, divided by a pressure of 1.00 ATM. Now, atmospheres, moles, and Kelvin cancel. In liters, I'm getting 24.5 on my calculator. To me, that would seem like a more useful number because we normally work at about 25 degrees Celsius, but lots of textbooks still like to use this molar volume at STP idea. Okay, thanks for tuning in. This is Morgan, signing off.